Greetings, folks. This video is being done primarily for the students who missed the discussion about the mass spectrometer, but clearly anybody who wants to know something about a mass spectrometer are welcome to watch. Enjoy. We start off with the charge Q. Accelerate it through a potential difference V1, giving it a velocity V. Have it pass through a velocity trap, which I will explain shortly, and have it move into this final chamber in which its interaction with the magnetic field will either motivate it to move in that direction like so, or this direction like so, depending on the direction of the magnetic field and the kind of charge we're looking at. So what can we do with this beast? We'll start with the far right chamber, which I've called the spectrometer. And the first question to be answered is, if the charge was positive, its velocity was in this direction, the magnetic field was into the page, in what direction would it be motivated to move as it passed into this cavity? We know that the relationship that governs the force on a charge moving through a magnetic field is QV crossed into B. Using the right-hand rule, we get V crossed into B at this point, giving us a force that's up. In other words, the body would begin to follow an arc that was upward. When it was right here, V cross B would give you a force in this direction, which was clearly centripetal. And if you continued checking along the way, what you would find would be what's more, if you had a fluorescent screen set up over here like so, that was calibrated, you could actually read off what the radius of that arc would be. So knowing the radius of the arc, the magnitude of the B field, the size of the charge, and the velocity of the particle, you could use Newton's second law to write a relationship from which you could determine what the mass of the particle was. This is the forensic tool called a mass spectrometer used in CSI units to determine the mass of unknown substances. In the TV show NCIS, it's what Abby, the forensic specialist, calls her baby. This question won't be on the test, but it will allow you to understand how the particle picks up the velocity that it has, how you can derive that velocity, and more importantly, why it's necessary to have a velocity trap in the system. So I'm fairly sure that in real spectrometers, the particle is singly ionized by plinking off an electron, leaving it electrically positive. That positive charge is accelerated through this potential difference, which is what gives it its velocity. As work is done on the charge, we can use energy considerations to analyze the situation. If we write out the conservation of energy for the situation, we can solve for the velocity that the particle will have when it leaves the acceleration unit. The problem is that as thousands to millions of particles jostle their way through this potential difference, there are going to be collisions. Some particles are going to pick up more energy than they would be expected to have. Some will have less, which means you're actually going to have a velocity range as the particles leave. The question arises, how do you select out just one velocity? This is where the velocity trap comes in. Velocity trap comes after the accelerator and before the spectrometer, and is a region in which there exists magnetic field and an electric field generated by charge on parallel plates. And I haven't shown you the direction of the electric field here because that's something you're going to have to figure out. The idea is that as your charge interacts with both the magnetic field and the electric field as it's moving through this region, if it's moving too slow, maybe it'll do something like that. If it's moving too fast, maybe it'll do something like that. But if it's going just the right speed, it'll be able to go on axis and pass right straight through. Which brings us to the next question. In what direction does the electric field have to be in between the plates for this to work? Or what kind of charge do you need on the top plate? To determine that, you have to think about forces. We've already figured out from looking at the magnetic field's interaction with the charge in the spectroscope part that if it was just a magnetic field in this region, this charge would go up, which is to say the magnetic force would be upward. So in what direction would the electric field have to be so that the force on a positive charge due to that field would be opposite the direction of the force due to the B field. Because if we knew that electric field direction, we would know what kind of charge would have to be on the top plate. Well, if the magnetic force is upward, the electric force must be downward. To get a downward electric force on a positive charge, you need a downward electric field. And here we have the field lines. That means the top plate has to be electrically positive. Next question. How are the electric field, the magnetic field, and the velocity related? This is something we can get, again, by looking at the forces acting on the particle. We've got a magnetic force up. We have an electric field force down. Summing up the forces, QVB minus QE, QE being the force on a charge in an electric field, equaling MA, which is 0 in this static situation, gives us what the velocity has to be in terms of E and B. So, in a nutshell, we have the acceleration unit, which accelerates the particle through a potential difference, ending up generating a range of velocities because we've got a whole bunch of particles coming through. Ignoring particles that are initially moving off axis and just looking at particles that are moving down the axis as they enter the velocity trap, one of three things is going to end up happening once they get into the velocity trap. Particles with velocity that's too big will have QVB overwhelm QE, the electric force. The particle will do that and it will never get through the trap. Particles with velocity too small will have QVB being too small. QE will govern. They'll do this kind of thing and they'll never get through the trap. Particle whose velocity is equal to E over B will move right straight down the axis and out through the aperture. Once into the spectrometer, the charge will end up going this way or this way, depending on whether it's a positive or negative charge, and depending on whether the magnetic field goes into or out of the page. And the radius of that arc will be related to the mass of the particle. So, possible test question. You could have a positive or negative particle, my choice, of given velocity moving into a velocity trap. There will be a known magnetic field, again my choice, either into the page or out of the page, that will permeate the space. First question, in what direction will the electric force on the particle have to be when in the trap? This is obviously going to be opposite the direction of the magnetic force when the particle's in the trap, which is something that you should be able to figure out. Knowing the direction of the force on the charge, you ought to be able to figure out the direction of the electric field in the trap. So if it's a positive charge, the field's going to be in the direction of the force. If it's a negative charge, the field's going to be opposite the direction of the force. You should be able to figure this out. Once you know the electric field, you ought to be able to figure out the charge on the top plate. You should be able to derive the relationship between E, B, and V. Don't just memorize it, be able to derive it. Should be able to use QV crossed into B in a right-hand rule to determine how the particle is going to travel when it gets into the spectrometer. It's either going to go this way or this way. You ought to be able to use the right-hand rule to figure that out. Given the radius of the arc in the spectrometer, you should be able to derive an expression for the mass. This is basically a Newton's second law and centripetal acceleration problem. As an alternative, I could give you the mass of the particle and ask you to derive an expression for the radius of the arc. Lastly, I should like to note that problem 1936 in your book is very similar to at least some of what we've been talking about here. So if you want to go and look at an actual PDF, that would be a place to go. That's it, folks. Enjoy.